The hydrogen nucleus in a molecule is surrounded by an electron cloud. This cloud shields the nucleus from the full strength of the external magnetic field and shifts the resonance frequency of the proton. A high resonance frequency in the downfield region of the spectrum indicates that the hydrogen is poorly shielded. A low resonance frequency in the upfield region of the spectrum indicates that the hydrogen is well shielded. The chemical structure of a molecule affects the amount of shielding of a hydrogen, and hence its resonance frequency. We can determine what kind of hydrogen gives rise to an NMR signal from its position in the spectrum, its chemical shift. Electronegative substituents decrease the shielding of a hydrogen by withdrawing electrons through the sigma bond. The more electron withdrawing a substituent, the further downfield the NMR signal of the deshielded hydrogens. Only substituents on the same carbon center significantly affect proton chemical shifts. Protons on unsubstituted aliphatic carbons have a chemical shift between 0.8 and 1.7 ppm, with CH3 protons at the lower end and CH protons at the higher end of this range. Weakly electron-withdrawing substituents shift the signal downfield to about 1.6 to 2.8 ppm. Strongly electron-withdrawing substituents cause a shift to between 3.1 and 4.7 ppm. Multiple substituents can shift the signal even further, such as in chloroform, which resonates at 7.27 ppm. In aromatic systems, the external magnetic field causes the pi electrons to circulate. The so induced local magnetic field strongly deshields the hydrogens directly attached to the ring. This causes a drastic downfield shift of their resonance frequency. In molecules with double bonds, a similar but smaller effect occurs, leading to a smaller downfield shift. Molecules with triple bonds have their hydrogen atoms oriented differently with respect to the induced local magnetic field, resulting in a relatively low resonance frequency. The hydrogens of benzene resonate at 7.3 ppm. Substituents influence the chemical shift of aromatic protons by donating or withdrawing pi electrons, which differs from aliphatic systems. Substituents that contain lone electron pairs donate electron density into an aromatic ring. This shifts the resonance frequency of the aromatic hydrogens upfield, especially at the ortho and para positions. Substituents that possess a CO or NO double bond at the attachment site withdraw electron density from the ring and shift the resonance frequency of the aromatic hydrogens downfield, especially at the ortho and para positions. The local magnetic field of the substituent pi bond further deshields the ortho protons. The hydrogens of ethene resonate at 5.25 ppm. In vinylic systems, a substituent affects the hydrogen at the same carbon center through the sigma bond as in aliphatic systems, and the hydrogens on the adjacent carbon center through the pi bond as in aromatic systems. Oxygen is a strong sigma-withdrawing substituent and shifts the resonance of the geminal hydrogen far downfield. Oxygen is a pi-donating substituent and shifts the resonance of the cis and trans hydrogens upfield. A carbonyl group is weakly sigma and pi withdrawing. The resonances of all three vinyl hydrogens are shifted downfield. This chart summarizes the chemical shifts observed for protons associated with pi systems. Note that aldehydic protons are shifted furthest downfield due to the strong electron withdrawing effect of the carbonyl oxygen combined with the local magnetic field of the double bond. A third factor that influences the chemical shift of a hydrogen is its ability to undergo hydrogen bonding. This is the case for protons attached to oxygen or nitrogen, such as in alcohols, amines, amides, and carboxylic acids. In a dilute solution, and using a solvent that cannot form hydrogen bonds, a hydrogen bonding molecule exists as monomer. As the concentration increases, intermolecular hydrogen bonding occurs. The hydrogen-bonded proton experiences a strong electron withdrawing effect, which increases its resonance frequency. The chemical shift of protons that can engage in hydrogen bonding varies over a wide range. Experimental conditions, such as solvent and concentration, play a large role. Another factor is acidity. Weakly acidic protons, such as in alcohols, resonate at relatively low frequencies. Strongly acidic protons, such as in carboxylic acids, are surrounded by less electron density and resonate at relatively high frequencies.